Welcome to the Bodhi Academy. My name is Amisha Plaso, and in today's video we will continue with our class 12 chapter 3 chemical kinetics. So last class we talked about some of the effects of that happen on the rate of reaction. In that we spoke majorly about the activation energy, the Arrhenius equation, how also we discussed about the temperature dependence of the rate of the reaction that happens. In that we discussed about activation energy, the Arrhenius equation, and also the kinetic energy, how it varies in every situation. Now today next we are going to look at the effect of a catalyst. So now what is a catalyst? So catalyst is basically a substance that increases the rate of the reaction without actually being involved in the reaction. Okay, so even if it is present in the reaction, it won't participate in the reaction. Okay, it will just increase the rate of the reaction without participating. So a catalyst is a substance which increases the rate of a reaction without itself undergoing any permanent chemical change. So the catalyst is not changing at all. It remains in its original form throughout the reaction, but it just increases the rate of the reaction. Now for example, MnO2 catalyzes the following reaction so as to increase its rate considerably. So here we have an example of potassium chlorate, and MnO2 is the catalyst that acts upon this reaction. This potassium chlorate decomposes to form potassium chloride plus oxygen. Now the word catalyst should not be used when the added substance reduces the rate of reaction. Now if we are having MnO2 as the catalyst, okay, and when we say it is a catalyst, it should increase the rate of the reaction. If it is decreasing, in that case it is no longer a catalyst but it is known as a inhibitor. So the action of the catalyst, it can be explained by the intermediate complex theory. Now according to this theory, a catalyst participates in a chemical reaction by forming temporary bonds with the reactants, resulting in an intermediate complex formation. So now what happens is that to understand this working of catalyst, one theory was proposed, and that was the intermediate complex theory. Now in this theory what is said was that as the reaction proceeds, the catalyst participates in the chemical reaction by forming a temporary bond, as in it bonds with the major substrate or the reactant that is there, and it forms an intermediate that is very temporary. It is short lived. After some time it will non-exist and it will leave the reaction. So this has a transitory existence and it decomposes to yield the products and the catalyst. So as we proceed further, we get the decomposed products as well as the catalyst is reverted back. Now it is believed that the catalyst provides an alternate pathway or a reaction mechanism by reducing the activation energy between the reactants and products, and hence lowering the potential energy barrier. So now what is happening by forming this intermediate, what it is doing, it is giving, first it was, say the reaction was going in a straight line, nothing was happening in between, directly reactants to products. Now what is happening here, there is an intermediate, so one step has increased, correct? So there is an alternate path that is being generated. So in that what happens, on this generation of this alternate path, the activation energy between the reactants and the products, it is reduced. Okay, so once that is reduced, then the potential energy barrier that was there, that also reduces, and this we can see in this graph. So initially without the catalyst, this was the activation energy curve. Now on using the catalyst, if you see, the activation energy has significantly decreased and so has the potential energy. So it is clear from the Arrhenius equation that lower the value of activation energy, faster will be the rate of the reaction. So a small amount of catalyst can catalyze a large amount of reactants. A catalyst does not alter the Gibbs energy, that is delta G of a reaction, it remains same. It catalyzes the spontaneous reactions but does not catalyze non-spontaneous reactions. So it is also found that a catalyst does not change the equilibrium constant of a reaction, rather it helps in attaining the equilibrium faster. So what we are trying to say here is that catalyst, firstly it does not alter the Gibbs free energy, secondly it works only on spontaneous reaction, it does not catalyze non-spontaneous reaction, thirdly it does not change the equilibrium constant, rather it makes the reaction reach equilibrium stage faster. That is, it catalyzes the forward as well as the backward reaction to the same extent, as in it creates a perfect balance between both, so that the equilibrium state remains same but it is reached earlier. Now let's talk about this collision theory of chemical reactions. Though Arrhenius equation is applicable under a wide range of circumstances, collision theory, which was developed by Max Strauss and William Lewis in 1916 to 1918, provides a greater insight into the energetic and mechanistic aspects of reaction. It is based on the kinetic theory of gases. So now, according to this theory, what it says is that the reactant molecules are assumed to be hard spheres and the reaction is postulated to occur when the molecules collide with each other. So now what they are saying is that they have said that they assume that the reactant molecules which are there, they are basically hard spheres, okay, and the reaction only occurs. So say there is A here, then there is B, then again there is A molecule, there are some molecules but all of them are hard spheres. Now they are saying that the reaction only occurs when any of these two collide with each other. So the number of collisions per second per unit volume of the reaction mixture is known as the collision frequency. Another factor which affects the rate of chemical reactions is known as the activation energy that we have already studied. So what we are saying is now that it is also affected by the collisions or the number of collisions that occur. Now for a bimolecular elementary reaction, A plus B giving products, rate of reaction, it can be expressed as what? Rate equals to Z AB e raised to minus E upon RT. So now what we can say, when ZAB, what does it say? It represents the collision frequency of reactants A and B, and E minus EA upon RT, it represents the fraction of molecules with energies that are equal to or greater than EA. Now if you compare the Arrhenius equation, we say that A is related to the collision frequency. In Arrhenius equation we were having A factor over here, so that now we are relating it to the collision frequency. So equation 3.23, this equation predicts the value of rate constants fairly accurately for the reactions that involve atomic masses or simple molecules, but for complex molecules significant deviations are observed. So now this equation we are saying it can be used for simpler molecules, but if we use this equation for complex molecules where there are n number of steps that are happening and n number of collisions that are happening, in that case this might give a deviation in the actual value. So the reason could be that all collisions do not lead to the formation of products. So the collisions in which molecules collide with sufficient kinetic energy, that is known as the threshold energy, and proper orientation so as to facilitate breaking of bonds between reacting species and formation of new bonds to form products are known as effective collisions. Now what we are saying, say two molecules are colliding, A and B. Now just because they are colliding does not mean they are going to lead further move towards the formation of any product, okay. They have just collided with each other, but there is no further formation of products that is happening. So that is why it is important for the collision to occur in a perfect orientation, okay. It depends on how it collides and where it collides, with how much energy it collides. So all these factors are important. Only when all these factors are considered and there is a formation of new bond or a new product, then it is known as an effective collision. Now for example, if we see at the formation of CH3Br plus OH over here, bromo methane plus OH giving us CH3OH plus bromide. Now here there can be two orientations that happen. So first let's look at the improper orientation. What does it say? That this Br is in this direction, okay. So they are not colliding with each other, they are basically colliding in some other direction. So when such things happen, there is no product that will be formed. Now in this case, if you see this and this, if they collide in the same direction, there will be an intermediate where all of them are going to be bonded with each other. Now once they are all bonded by each other, this intermediate needs to be highly stable. Now it is highly stable, why? Because carbon has a valency of only 4 bonds, it can form 4 bonds. So here now it is forming 5 bonds. So the minute it forms 5 bonds, it is highly unstable and it would want to break one of the bonds so that it attains stability. So that is what is happening here. It decides to break a bond with this bromine over here, and we get this two products as the end results. So now if we say methanol from bromoethane depends upon the orientation of reactant molecules as shown. So now the proper orientation of reactant molecules, it leads to bond formation, whereas improper orientation makes them simply bounce back and no products are formed. So that is what happens in improper orientation. There is a bouncing back and no further products are formed. Now to account for effective collisions, another factor is P called as the probability or steric factor is introduced. So it takes into account a factor that in the collisions molecules must be properly oriented. If they are not oriented in the right direction, in the right manner, no collisions will occur, and further no reaction or no products will be formed. So rate equals to, so we add the P factor, that is the probability or the steric factor, PZAB e raised to minus Ca upon RT. So thus in a collision theory, activation energy and proper orientation of the molecules together, they determine the criteria for an effective collision to occur, and hence the rate of a chemical reaction. Collision theory is certainly said to have certain drawbacks, but when we consider that they are only hard spheres and we ignore rest of their structural aspects. But about this we will learn in the higher classes. For now, this was it for the whole chapter of chemical kinetics. I hope you have understood. Please don't forget to like, share and subscribe to the Bodhi Academy. Thank you.